Hi everyone, welcome back to another video of our Ethereum series. In this video, we'll cover EVM in detail. So, EVM exists as one single entity that is maintained by thousands of connected nodes running an Ethereum client. It is based on a simple stack based architecture. So, a distributed ledger is often used to describe the blockchains like Bitcoin. These distributed ledgers enable a decentralized currency using some fundamental tools of cryptography. This distributed ledger maintains a record of all of the activity happening on the network, and this activity must adhere to a set of rules that govern what someone can and cannot do to modify the ledger. For example, a Bitcoin address cannot spend more Bitcoin that it has previously received. This is commonly called double spending, that you are trying to spend something that you don't really have. So, all of these rules, or you can say a system design, that there will be some accounts they can transfer some value between themselves and they can hold some value in their accounts. The value that they are sending shouldn't exceed more than the value that they already have in their accounts, and some other rules. So, all of these rules make up a distributed state of the blockchain, and it really decides what can or cannot be done on the blockchain. So, Ethereum goes a little bit ahead of Bitcoin, and it enables smart contracts as well. So instead of just a distributed ledger like Bitcoin, which keeps a record of all the transactions happening on the blockchain, Ethereum is also a distributed state machine which allows you to run your own program or interact with programs that someone else has already deployed. Ethereum's entire state is a large data structure that holds all of the account and their balances, but it's also a machine state which can change from one block to another block according to a predefined set of rules. This change is brought about by executing an arbitrary machine code, and the specific rules of changing state from block to block are defined by the EVM, or Ethereum Virtual Machine. So we have a simple state transition function which takes in the old or the current state of EVM and a set of valid transactions, and it creates a new state, a new valid state of EVM by applying those transactions to the previous state. The state is an enormous data structure called a modified Merkle-Patricia tree, and it keeps all of the accounts linked by hashes and is reducible to a single root hash that is then stored on the blockchain. A very raw form of Merkle Patricia tree looks like this. The data is stored in the leaf nodes, and the leaf nodes are then hashed together recursively until a top hash is derived. This is called the root hash, and this is stored on the blockchain. As we have already covered in one of our previous videos, transactions are cryptographically signed instructions from accounts. There are two types of transactions, those which results in message calls and those which result in contract creation. So contract creation results in the creation of a new contract, and this new contract account contains the compiled smart contract bytecode. Whenever another account makes a message call to that contract, it executes its bytecode according to the instructions sent by the account. This execution leads to a change in the state of EVM, and as we discussed, when this transaction is applied to a previous state, it creates a new state of the EVM. So EVM is a stack machine with a depth of 1024 items. If you're not familiar with the concept of stack machine, do check it out on YouTube or Google or ChatGPT. But stack machine is essentially used in most of our computational devices. So it is a stack machine with a depth of 1024 items, where each item is a 256-bit word. It was basically chosen for the ease of use with 256-bit cryptography such as Keccak 256 hashes or some other signatures. During the execution, EVM also maintains a transient memory, which is a word addressed byte array, and it does not persist between transactions. So, this memory exists only while the transaction is executing. When the transaction is finished executing, this memory is cleared out. Apart from memory, contracts also have a Merkle-Patricia storage tree, which is a word addressable word array. And this storage tree is associated with the account in question and is also a part of the global state. So it is a part of the state of the blockchain. So the compiled smart contract bytecode is actually a list of EVM opcodes trying to do some kind of operation. And whenever a user initiates a transaction request, these EVM opcodes perform standard stack operations like AND, add, subtract, etc. etc. So it works something like this. We have a stack machine of depth 1024 items, and we have a memory which is only persisted for the duration of the transaction execution. Apart from that, we have a storage which is persisted as a part of the global state. So this is a sort of permanent storage, and this is a sort of transient and temporary storage. So whenever an EVM opcode executes something, let's say we have add something and something, so this data could be loaded from the transient memory into a stack machine, or this data could be loaded from the permanent storage into a stack machine. Then the relevant operation is performed on those data. For example, we have two chunks of data here. These would be loaded from either of these memories, and the operation would be performed on these data. And then the result would also be stored on the stack, and it would be used according to the EVM opcodes following this opcode. So this is a very crude overview of how this EVM stack machine works. When it comes to EVM, there are a lot of things, a lot of nuances that I'll need to cover. So I have created a separate part just for EVM and opcodes, and it will be going live soon. But for now, this much information is enough for you to go ahead with. EVM also has some blockchain specific stack operations like address balance, block hash, etc. So, for example, using block hash, you can get the hash of the current block, and using address, you can get the address of the account who has initiated the transaction request. So, for all of the opcodes supported by EVM, you can check out this cool resource called evm.codes. And here you will find a list of all of the opcodes that is supported in EVM, and you can read a lot of data about them, like what is the opcode, what is the name of the operation, how much gas it would take, what are the inputs that it will need, and what would be the resultant output. Do check out this website. It will help you a lot in understanding EVM opcodes. Lastly, we have EVM implementations. So all of the implementations of the EVM must adhere to a specification described in the Ethereum yellow paper. So in the start of video, we talked about certain rules governing the system and deciding what a blockchain can do or cannot do. So all of these rules combine together to form an EVM specification which is described in the Ethereum yellow paper. And this technical specification is then implemented by multiple Ethereum clients in their own language like C++, Rust, Go, Python, etc. So you have multiple clients like Git, Nethermind, etc., each implementing the EVM specification in their own way. So that was all about EVM. In the next video, we'll cover gas in detail.